Okay, so this particular problem, we now have some numbers, and he wants us to solve the equation that we derived in the last one, which is this right here. Well, let's just go ahead and start plugging some stuff in, see what we get. We get 10 times negative 3 di dt. This is all in terms of IL, so I'm not going to bother writing the L. We all know by now that I is a function of t, so I'm not going to bother writing that either. I'm just going to write it as a simple variable. So I times R1, R2 is 4, divided by R1 plus R2 is 5, which equals 12 volts. Okay. So how do we solve this? We've got 10 to the negative 2 di dt plus 4/5 I equals 12 volts. The general solution that we're supposed to use for this is K1 plus K2 equals ST S equals it's negative 1 over tau. Tau is what he actually wants us to find. He does not care about S, but since my taus tend to look more like 2s, I'm going to keep working with S and then just convert it back at the end. K1, K2, of course. Alright, so let's plug this equation back into here, into this differential equation. We get 10 to the negative 2 times K1 plus K2 oh dear, no, what am I doing? I'm not deriving anything here, am I? Okay. S K2 EST. Okay, this is our first part. Plus I is K1 plus K2 EST equals 12 volts. Honestly, this is kind of a piece of cake. The ESTs are time dependent. The answer is not time dependent. So they somehow either have to cancel each other out in order to make this all not time dependent. Alright, but we'll look at that in a second. What we also know is, oh dear, I forgot to, there should be a 4/5 here. Forgot about the resistance. But what this also tells us is that K1 is the only part that is not time dependent at all. Therefore, gotta do our distribution. 4/5 K1 is equal to 12 volts. K1 equals, should be 15? Yeah, 15A. Because it's a constant that will produce current. So, 7A. Alright, then, so we've gotten rid of this, we've dealt with this. So we got rid of this and this because they were equal to each other. We took them out, we took them aside. So we've got 10 to the negative 2 SK2 EST plus, this should be K2, plus 4/5 K2 EST equals 0, because that's the only way to get rid of time dependent parts is to basically put them to 0. Okay, so we've got 10 to the negative second SK2 plus 4/5 K2 equals 0. We still have two constants here. I'm sure there is some generally known function for tau that has to do with inductors, like normally you use RC as the time constant, but obviously we don't have a capacitor here, and I have no idea what that function is. So, instead we're going to look at and try and find K2 first. Well, if we look at the function K1 plus K2 EST, alright, we've already derived at time 0. This is our I. At time 0, I of 0 equals, let's see, what was it? 3a. Because the inductance is because the voltage of an inductor is L times the derivative of IL, there can be no sudden jumps because we can't have current looking like this, where this is time and this is current. We can't have like some number here and then all of a sudden some number here, because the slope here is basically infinite. And that would give us infinite voltage, and that's not possible. So we cannot have jumps in I. So we can assume that before 0, if I is at 3, then at 0 it's still going to be at 3. It might all of a sudden change the function or whatever, but I itself is not going to jump. So I of 0, even after the switch is closed, is still 3a. Okay, so R times 0 is 3a, which means that k1 plus k2 times e to the 0 is equal to 3a. Well, we already know k1 is 15a. I'm sure you can all do this algebra. k2 is negative 12. Alright, so now we're going to go plug this back in way down here. Alright, we plug this back in. S times 10 to the negative second times negative 12. That's 0.12 S plus 4/5 negative 12. Let's see. Um, 0.12 S equals 48/5. Let's get rid of this by multiplying by 0.12. And your number comes out to be